For nearly a century, scientists believed they had the most accurate blueprint of the universe ever created. From the moment the Big Bang occurred, about 13.8 billion years ago, through the formation of the first galaxies, stars, planets, and eventually life itself, everything seemed to fit within a single framework. It was called the Standard Model of Cosmology, more commonly known as the Lambda-CDM model. It was the result of decades of observations, thousands of scientific papers, and countless independent tests. Thanks to this model, we can predict the faint afterglow left behind by the Big Bang, explain how galaxies formed, and even describe the evolution of the entire universe with astonishing precision. In science, very few theories have been this successful. And yet, over the past decade, what seemed like a minor discrepancy has begun to shake that confidence. More and more, the debate in cosmology has centered on a single number: the expansion rate of the universe. According to the theory, no matter how you measure it, that number should always be the same, because the universe has only one evolutionary history. But reality refuses to cooperate. The two most precise methods available today consistently produce different answers. The difference is only a few kilometers per second, but its implications are enormous. Put simply, for every 3.26 million light-years of distance, galaxies appear to recede roughly 67 to 74 kilometers per second faster. The problem is that the two leading measurement techniques cannot agree on exactly where, within that range, the true value lies. That raises an unsettling question. Could the model we use to describe the entire history of the universe be missing a crucial piece? That question became even more urgent when the James Webb Space Telescope began operations. Built at a cost of roughly $10 billion, Webb was expected to serve as the ultimate referee, powerful enough to determine which side was right. Instead, what it saw made the debate more complicated than ever. The number we're talking about is called the Hubble constant. It tells us how fast a galaxy is moving away from us based on its distance. So, if this number is 70, here's what that actually means. A galaxy located 1 megaparsec away, that's about 3.26 million light-years, is moving away from us at 70 kilometers per second. A galaxy 2 megaparsecs away would be moving away at 140 kilometers per second. If we know this number, we can work backward through cosmic history to estimate the age of the universe, determine when the first galaxies formed, and test whether our cosmological model truly matches what we observe. The problem is that the Hubble constant can be measured in different ways, and the two most precise methods give different answers. The first method is like looking at a snapshot of the universe when it was still an infant. Scientists use data from the Planck satellite, operated by the European Space Agency, to observe the cosmic microwave background the ancient light released, when the universe was only about 380,000 years old. From those faint remnants, they feed the measurements into the Lambda-CDM model and calculate how fast the universe should be expanding today. The result is about 67 kilometers per second per megaparsec. The second method is completely different. Instead of looking deep into the distant past, the SHOES team, led by Nobel Prize-winning physicist Adam Riess, measures the distances to relatively nearby galaxies directly. They use the Hubble Space Telescope to observe Cepheid variable stars and type Ia supernovae as cosmic distance markers, building what astronomers call the cosmic distance ladder. By combining those distances with the speeds at which the galaxies are moving away from us, they arrive at a different value, about 73 kilometers per second per megaparsec. Both teams spent years reanalyzing their data, recalibrating their instruments, and searching for possible sources of error. Yet the results barely changed. At that point, many scientists began to suspect that the problem might lie with the Hubble Space Telescope itself. When Hubble observes Cepheid stars at great distances, the light from multiple stars can blur together. This effect, known as stellar crowding, can make a star appear brighter than it really is, leading to inaccurate distance measurements. If that were the case, the entire SHOES result would shift downward, much closer to the value predicted by Planck. That is exactly why the James Webb Space Telescope was expected to settle the debate. With its infrared vision and far superior resolution, James Webb can resolve individual stars that Hubble could never separate. If stellar crowding were truly responsible for the discrepancy, Webb would reveal it. But what happened next was the exact opposite of what scientists expected. After re-observing the very same Cepheid stars that Hubble had used, James Webb found that Hubble's earlier measurements showed almost no significant bias. In other words, the problem was not with the Hubble Space Telescope. Following the James Webb results, the debate was no longer about who had made a mistake. If Hubble wasn't wrong, and James Webb confirmed the same measurement, then what was really going on? That was when another key figure entered the story, astronomer Wendy Friedman. For many years, she pursued the same goal of measuring the universe's expansion rate. But instead of using Cepheid variable stars like the SHOES team, Friedman relied on red giant stars in the final stage of their lives. These stars are located in the outer regions of galaxies, where there is less dust and less stellar crowding, making them more reliable distance indicators. Later, she added another distance marker known as JAGB carbon stars. Because these stars have remarkably uniform near-infrared brightness, astronomers can determine their distances from a single observation, rather than spending months monitoring the pulsation cycles of Cepheid stars. Combining these methods with the razor-sharp data from the James Webb Space Telescope, Friedman's team measured the Hubble constant at roughly 70 km per second per megaparsec, almost exactly halfway between the two competing values. At first glance, this seemed like the solution to the crisis, but reality turned out to be far more complicated. Friedman's result did not prove that Planck was wrong, nor did it disprove the SHOES measurement. 3 independent methods, each subjected to rigorous testing, were producing 3 answers that did not completely agree. Perhaps the problem wasn't with the measurements at all, but with the model we used to interpret them. Nobel Prize-winning physicist Saul Perlmutter has suggested that our cosmic distance ladder may still contain a missing or poorly understood link. But there is an even more provocative possibility. What if all 3 groups are right? If every measurement is accurate, then only one explanation remains. The universe may not behave exactly as the standard model of cosmology assumes. One of the leading ideas is called early dark energy. According to this hypothesis, shortly after the Big Bang, the universe may have experienced a brief period during which a mysterious form of energy temporarily accelerated the expansion of space. It then disappeared before the first galaxies formed, leaving behind almost no trace except the discrepancies we observe today. In other words, the standard model may be missing an entire chapter from the earliest moments of cosmic history. But while theorists continue debating what that missing chapter might be, James Webb has been sending back observations that make the situation even more puzzling. This time, the mystery is no longer the expansion rate of the universe. It is the very first galaxies that appeared after the Big Bang. The telescope's original mission was fairly simple: to look farther than any telescope before it and observe the very first galaxies that formed after the Big Bang. But the farther James Webb looked, the more astonishing its discoveries became. Roughly 500 to 700 million years after the Big Bang, it found numerous galaxies that appeared to have evolved far too quickly. They were brighter, larger, and seemed to contain far more stars than the standard model of cosmology predicts. It was like finding a 3-year-old child with the physique of a professional weightlifter. It's not impossible. But if you keep encountering children like that, perhaps the problem isn't with the children themselves. Perhaps it's with our understanding of how growth is supposed to happen. If these galaxies really were as massive as the initial estimates suggested, they would have had to convert nearly 100% of their available gas into stars within just a few hundred million years after the Big Bang. Yet, according to current models, galaxies are expected to convert only about 10% of their gas into stars. That is an enormous gap. Yet astronomers did not rush to conclude that the standard model was wrong. Instead, they searched for simpler explanations. One of the most compelling came from Katherine Swarovski and her collaborators. They found that many of the objects James Webb had detected were not actually the giant galaxies they first appeared to be. At their centers were supermassive black holes, consuming matter at extraordinary rates. The intensely heated gas around them emitted so much light that it made the entire galaxy appear both brighter and more massive than it truly was. These objects became known as little red dots. This discovery solved part of the mystery. Many of the earlier estimates of galaxy masses had been exaggerated. It seemed as though the crisis was finally beginning to fade, but only partly. Even after accounting for the influence of the little red dots, new surveys still found roughly twice as many massive galaxies in the early universe as theoretical models predicted. In other words, the new explanation narrowed the gap. It did not eliminate it. And then James Webb uncovered even more puzzling cases. Some galaxies had already developed fully formed spiral structures only a few 100 million years after the Big Bang, even though simulations suggest such orderly structures should have taken much longer to emerge. This suggests that galaxy formation during the earlier stages of cosmic history may have unfolded differently from what we have long assumed. By this point, many researchers had begun to notice a common pattern. The Hubble tension was one clue. Galaxies maturing far earlier than expected were another. Each phenomenon, taken on its own, might still be explained. But as more and more independent clues began pointing in the same direction, the question was no longer, which discovery is correct? Instead, it became, are we missing a crucial part of the story of how the universe evolved? After all, Lambda-CDM remains the most successful model ever built in the history of cosmology. From the cosmic microwave background and the distribution of galaxies to the evolution of the universe over billions of years, most of what we observe still agrees remarkably well with its predictions. And that is precisely why today's contradictions are so significant. By the end of the 19th century, classical physics seemed to explain almost every phenomenon in nature. Yet a handful of results that didn't fit eventually paved the way for two major revolutions: relativity and quantum mechanics. Then, near the end of the 20th century, observations of distant supernovae led to another, even more surprising discovery. The universe was not only expanding, but expanding at an accelerating rate. The concept of dark energy was born from that discovery. Perhaps what we are witnessing today is simply a measurement error that will soon be resolved with better observations. But perhaps these are the first signs of another revolution in cosmology. Maybe one day, all of these measurements will converge on the same answer, or perhaps they will force us to rewrite part of the standard model. Today, thousands of scientists around the world are still debating whether the universe is expanding at 67 or 73 kilometers per second per megaparsec. But that seemingly small gap could determine whether we simply need to refine a few measurements, or whether we are standing at the threshold of an entirely new chapter in cosmology. Because in the end, the universe has never changed. What is changing is the way we understand it.